Alright, so in this video we're going to talk about dimensional analysis. Now we talked about dimension in the previous video, so this time around we're going to talk about dimensional analysis. Now dimensional analysis is simply just a way of applying the knowledge of dimension to solve problems. Understand? So in this concept we're going to discuss the applications of dimension. What can we use dimension to do? That is the analysis, the dimensional analysis. So the first thing we can talk about, or the first thing we are going to talk about is it can be used to check for the correctness or homogeneity of a physical equation. So first, dimension to check the homogeneity or correctness of a physical equation. Now this is the first application. Now when we talk about homogeneity from English language, when we talk about homogeneity simply means the quality of being of the same kind. If I have an object A and I have another object B, they are homogeneous if they are of the same kind. You understand? They're the same. If they are the same, they are homogeneous. You understand? Correctness is a very common English word. So it's used to check the homogeneity or correctness of a physical equation. A physical equation is just a normal equation where you can have something plus something equal to something. You understand? For instance, you can have A plus B equal to C. This is a physical equation. So we're going to try to solve an example to show you how you can use dimensions to determine the correctness of an equation. But before then, there are some rules you have to note down concerning dimensional analysis. And the first rule, so we have rules. Let's talk about some rules. The first rule is that you can only add or subtract physical quantities with the same dimension. Secondly, you can only add or subtract physical quantity with the same dimension. Yes. For instance, let's take A. A can be acceleration, the normal acceleration of a body. You have G. G can be acceleration due to gravity. You can only add them because they'll have the same dimension. It might not be only single. Probably if you have let's say two physical quantities, adding another two physical quantity. When you combine the dimension of these two, let's say it gives you LT. If you combine the dimension of these two, it's meant to give you LT also. Don't worry, don't rack your brain too much. When we get to the example, you see what I'm talking about. So you can only add or subtract physical quantities that has the same dimension or unit. You understand? So the second thing we're going to talk about is second rule is for an equation to be correct. For an equation to be correct, each quantity must have the same dimension or unit. for an equation to be correct, remember we said the first application is to check the correctness of an equation, right? Now, one of the rules says that for an equation to be correct, each quantity must have the same dimension. So if you have a relation like this, for this relation to be correct, each of the quantity must have the same dimension. So what we are just going to do is check the dimension of this, check dimension of this, check dimension of this. If the three has the same dimension, then we are correct. And the equation is correct, sorry. If they don't have the same dimension, the equation is wrong. The third thing we have to note is that in performing dimensional analysis, permit me to use DA as dimensional analysis, we ignore constants. We always ignore constants. An example of constants, whenever you have numbers like you can see 1 over 2 or 1 over 2 AB, you ignore this, you just work with this. So you can have 16 PQ, you ignore this, you just work with this, you understand? So down over to an example. Okay, so our first example says, using dimensional analysis, check if the equation S is equal to UT plus half AT is correct. Now, this seems familiar to most of us that study. I'm not going to talk where I got this equation from, but you're meant to know. You understand, from your O level. At the end of the class, then we'll talk about the equation. So using dimensional analysis, check whether the equation is correct. Now, if you're familiar with the equations of motion, okay, familiar with the equations of motion, you have seen this equation before. So now, let's say you're in the exam hall and you forgot one of the equations of motion, which is this. So you wrote out this. You now want to check, is it correct or am I wrong? Now, dimensional analysis helps you to determine that. So the first thing we're going to do is we're going to determine the dimension of each of the quantities. So we have S, U, T, and A. So these are all the quantities in this equation. Now remember I said in dimensional analysis, you don't make use of constants, one of the rules. So just take this out quickly. You're not working with that. So let's go back. Now the dimension of for S simply means distance or height. So S is a length. So the dimension of S is capital L. Now U simply means initial velocity. Now we know that velocity is equal to displacement over time. So displacement, which is S, the dimension is L. The dimension of time is capital T. So the dimension of velocity gives LT raised to power minus 1. When you apply indices, dimension of time is just capital T. Then dimension of acceleration, velocity over time. Now, since we know the dimension of velocity and time, there's no need going further. Velocity is LT minus 1 divided by T. Now, in your indices, according to indices, we are told that whenever something comes up, so this is LT minus 1 multiplied by this will come up and be T minus 1. Now, also in indices, when you have two similar quantities multiplying each other with different powers or similar powers, you add the powers. So this is LT minus 1 plus minus 1. Now, there's a video I dropped on science, a very short video. So if you watch that video, you understand what to do here. But regardless, whenever you have plus multiplying minus, it gives minus. So LT minus 1 minus 1, negative 1, negative 1. You borrowed 1k from someone, you went ahead again and borrowed another 1k. How much are you owing that person? You're owing that person 2k, so that's T minus 2. So the dimension of acceleration is LT minus 2. So we're done with the step 1 of the calculation. Step 1 is simply just to write out the dimensions of each of the quantities you have in the equation. Now this step 2 is going to be to replace each of the quantity with its dimension from the equation. So this equation now will become, let's quickly, so this equation will become L, which represents S, equal to, what is your U? Your U is LT minus 1, plus, remember we're not making use of a constant, so this is LT minus 2 multiplied by T. So we have L equal to LT, okay, yeah, UT, sorry, my bad, UT Okay, let's quickly write this on a straight line to avoid any form of confusion. So S, we have U equal to LT minus 1, we have T equal to T, and we have A equal to LT minus 2. So with this, we can erase from here, yeah, it's better. Now following up, we're going to substitute each of the dimensions for their quantities. So S remains L, U remains LT minus 1, T plus, remember you're not working with a constant, so just A, LT minus 2, and time capital T. So remember your indices. According to indices, when you have A3 multiplied by A2, this gives A3 plus 2. Understand? When you have two things multiplying, you add the powers. If it is division, you subtract, understand? So according to the law of indices, L remains L. Then in law of indices, LT minus 1, there's 1 here, so plus 1, plus LT minus 2 plus 1. Minus 1 plus 1 gives 0, so this is going to be, anything raised to power 0 is 1, so we're just going to left with L multiplied by 1, which is L, plus, now minus 2 plus 1 gives minus 1, so LT minus 1. Now we have come to the end of the dimensional analysis. Now from our dimensional analysis, we can see that the first quantity, we got half L, the dimension is L, second L, third is LT minus 1, meaning this equation is wrong, you can't use it. Do you understand? Now the correct equation, we're going to solve this again. Clean this. Now the correct equation is T square, half AT square. So let's try to use half AT square to see if would get a homogeneous equation or not. So same thing, L, U is LT minus 1, T is still T, plus, now A still remains LT minus 2, then T now becomes T raised power 2. Remember I said you are working, you don't use constants. There's a difference between index, this is an index, or a power. You make use of powers, but you don't use constants. When I mean constants, I mean coefficients. If you have a letter A, you have 2. This is the constant or the coefficient. You understand? You don't make use of this. If you have A square, you can make use of the power. So to finish this, you can quickly pause the video and quickly solve this, then get back to the video. So this is L, LT minus 1 plus 1 plus L T minus 2 plus 2. L equal to L, because minus 1 plus 1 gives 0. T raised to power 0 gives 1. 1 times L gives L. Plus minus 2 plus 2 gives 0. T raised to power 0 gives 1. And 1 times L gives L. So this is a dimensionally homogeneous equation. So in the exam, you can see that using dimensional analysis, you have determined what the actual equation of motion is. So the second thing we are going to, the second example we're going to try to tackle. I have a second question, number 2. The second application of dimensional analysis or dimension is to derive the unit of a physical quantity. Now this is very, very straightforward. When you know the dimension of something, you can easily get the unit. Now let's take an example. We solved a first example. So example 2. Now example 2, they say derive the unit of momentum using dimensional analysis. So we're talking about momentum. And we know that momentum, now for you to be able to do dimensional analysis very, very good, very effortlessly, you must know the formulas of most of the physical equations, you understand? So momentum is simply the product of mass times velocity. Momentum is represented with the letter P, capital P, equal to mass times velocity. So we know that mass, it's a fundamental, so we have to break down velocity, which is a derived. So velocity is displacement over time. That's it. This is fundamental. So the dimension is going to be capital M times distance. This is capital L over time. So the dimension is going to be MLT minus 1. Now from the dimension, you can easily get the units. The dimension M stands for mass, so the dimension of mass, the unit of mass, is kilogram. L stands for length, the unit of length is meter. T stands for time, the unit of time is second. So you can either write it like this, second minus 1, or you can say kilogram meter per second. This per also means raised power minus 1. So this is a use of dimensional analysis, or a use of dimension. So we go to the next question to better understand how we can use it to derive units. Now this is a bit long, but we're going to solve it. The viscous force between two layers of a fluid of liquid with surface area of contact A in a region of velocity gradient is given by F is equal to, this is the correct symbol, N A, the V over the X, where N is the coefficient of viscosity. Let's see, what is the dimension of N and what is the unit of N? Now, the first thing we are going to talk about is, the first thing we are meant to do is to make N the subject of the formula. Understand? So the first thing you're going to do is to simply divide both sides by A, the V over the X. Now, anytime you're solving for velocity gradient, the V over the X, please kindly take it as one entity. If you're moving it about, just take it as one entity to avoid confusion. this is the velocity gradient I'm talking about. We're not going to talk about it here now, but in subsequent topic, we're going to explain what velocity gradient is. So we're just going to divide both sides by the v over the x. Now this is going to cancel out this, so you're going to be left with, I know most of us have seen this equation before. We're going to be left with n, we're looking n equal to f over a the v over the x. This is your first step. The second step is to look for the dimension of each of the quantities. So the dimension of f, which is 4, I think we've calculated this before. We got mlt minus 2. Dimension of area, we got the dimension of area as L squared. Now the dimension of velocity gradient, now this is the v over the x. The v here stands for velocity, not this d, just v stands for velocity, x stands for distance. So the dimension of velocity, as we know before, is lt minus 1. Check from the previous video or from the previous example. Dimension of distance, x is the distance, is L. So the dimension for velocity gradient, this is going to cancel out this. Dimension of velocity gradient is t minus 1. So it's not that complex. So we have so for our velocity gradient, the v over the x is going to be t raised to power minus 1. Now I simply just substitute each of the dimensions for their actual quantity. So this is going to be m lt minus 2 divided by L square multiplied by t raised to power minus 1. Now we're going to be left with now you can cancel out some things. The L here will go and reduce this one to 1L. Then you're going to be left with m. Now this L is going to come up, which is going to be L minus 1. And your t is going to be, you still write this t, let's not walk too fast, multiplied by, now when this t comes up, the sign will change, it's not going to be t. So your final answer is going to be m L negative 1. Now minus 2, remember our indices, minus 2 plus 1 gives minus 1, so t raised to power minus 1. Now this right here is the dimension for this weird looking symbol, which is called coefficient of viscosity. So it's from getting the dimension of n, you can easily get the units. Now the units for m is going to be, m is kilogram, L is meter negative 1, second negative 1, or you can say kilogram per meter second, any one of your choice. So that's how you can use dimensional analysis to determine the units of a quantity. Understand? Now we'll move over to the third application of dimension. Now this particular one, you have to pay attention to really get it. Now the third application is to derive the relationship between physical quantities in an equation. To derive the relationship between physical quantities in an equation. Now, the best way to do this is to go straight to an example, solve an example, so you see how you can derive the relationship between physical quantities. Okay, so the question says, suppose a student is required to determine the period of oscillation of a simple pendulum, and he remembers that the factor on which the period depends on our length, mass, and acceleration due to gravity. That's it. He just remembers that these are the three things that the formula depends on, or that are contained in the formula, but he doesn't know how to represent the formula. He uses dimensional analysis to obtain the exact relationship between the displacement, acceleration, and time as follows. So he has a relation. T is equal to K L raised to power X. Okay, let's write it this way. So he has T is equal to K L raised to power X, M raised to power Y, and G raised to power Z. Now this is the relation he has, but he doesn't know the exact form. So we're going to solve this, and at the end of the video, you're going to see that this formula is very, very familiar. You know it, you understand? So the first thing we are meant to do is, as usual, look for the dimension of each of the quantities. So we have dimension for T. T stands for period. Understand? T is period. Look at it from the question. On which the period T stands for period, and period is time. Understand? Period is the time taken. Now when we talk of simple harmonic motion, we're going to talk about period. Well, period means time. So the time is still going to be capital T. Remember, we don't deal with constant. They say where K is a dimensionless constant, so we're not going to use this in our calculation. Constants can not only be numbers, sometimes they are letters. So it's a dimensionless constant. From the question, it is stated. So L is, they said L is length, so obviously it is really simple. M is mass, same dimension. Then G is acceleration due to gravity. Now in dimension, you start hearing a lot of strings. They can tell you speed of light, speed of oscillation, blah blah blah. The only thing you need to pick out is speed. You understand? You don't need to you don't need to remember any other thing or rack your head about any other thing. When you hear acceleration due to gravity, so far you have heard acceleration, you're working with the dimension of acceleration. Now, acceleration from our previous video, acceleration is LT minus 2. If you still don't know how to do this, go back to the first video. So the next thing we are going to do is to substitute each of them. So let's write it in the linear form. M stands for M, G stands for LT minus 2. So we're going to, just as we did in the first example, we're going to substitute each of them. So T still remains T. We're not using K, so now don't forget your powers. L raised to power X, M raised to power Y. Remember, these are not the M and L here. These are the dimensions, don't forget. Then G now is going to be LT minus 2 raised to power Z. Understand? Now, obviously, from indices, you have to, when you open the bracket, the power multiply in all the individual components of the bracket. So we're going to have L raised to power X multiplied by M raised to power Y multiplied by, now this Z is going to multiply both this and this. So we have L raised to power Z from indices, and T raised to power minus 2 times Z gives minus 2Z. So remember, from indices, these two are like terms and they're multiplying each other. So this is going to be L X plus Z. I think in the future I'm going to make a video on YouTube for indices to help us tackle problems like this. Multiplied by M raised to power Y multiplied by T raised to power minus 2Z. So having this now, is pay attention. There's something we are going to do now. something we are going to do now that might look a bit strange, but it's not strange, trust me. Now, if you look at from our previous discussions, we know that the three basic fundamental quantities are L, T, and M, right? Length, time, and mass. So in the third application of dimensional analysis, what you want to do is you want to make sure that both the left hand side, which is this side, and the right hand side has L, M, and T. The right hand side has it, so we are done with the right hand side, but the left hand side does not have it. So what are we going to do? Remember that anything raised to power 0 gives 1, right? Anything raised to power 0 gives 1, and anything multiplied by 1 gives that thing. So using this idea, we can do a little bit of mathematic, and we'll see that L raised to power 0 multiplied by M raised to power 0 multiplied by T gives us Lx plus Z multiplied by M raised to power Y multiplied by T raised to power minus 2Z. I don't know if you are still following. Because when you do this, L raised to power 0 gives 1, M raised to power 0 gives 1, 1 times 1 times T gives you back C. So the only thing we just did is try to make both the left hand side and the right hand side have L, M, and T, L, M, and T. You understand? There's no big deal here. Now the next thing we're going to do now the next thing we're going to do is to compare the powers. You understand? We're going to compare the powers. For L, we know we have L here, L here. So we're going to compare the powers. Now comparing the powers, we're going to have X plus Z equal to 0. Why did I say so? We have L here, we have L here. The power of L on the left hand side is 0. Power of L on the right hand side is X plus Z. Don't mind me, I just rearranged the equation. Now this is equation 1. Now we go over to the next. This one is for what? For L. For M, we're going to have Y is equal to 0. This is equation 2. Then thirdly, for T, remember T is carrying a power 1, don't forget. So we're going to have minus 2Z equal to 1. So this is equation 3. Yes, now we have the relation we are looking for, the 3 equations. Now solving these equations will help us determine the relations of the above quantities. So from our normal common sense, or from the idea of simultaneous, but this is not actually really simultaneous, we can make Z the subject here. So making Z the subject, we just divide both sides by minus 2. Z becomes minus 1 over 2. We can plug this Z back into the first equation. So we're going to have, from the first equation, X, when this crosses over to this side, this becomes what? Minus Z. Okay, let me go this way. Okay, yes, X becomes minus Z. So X now is equal to negative, don't forget, you have another negative here, minus 1 over 2. X now becomes negative multiplied by negative gives positive. X is now 1 over 2. And don't forget your Y is equal to 0. So we have gotten the value for X, Y, and Z. Now all you have to do is just to substitute them back into your original equation, into this relation here. So the aim is just to use dimensional analysis to get your A, your X, Y, and Z, to get your powers. Then you can work out the rest by yourself. It becomes very, very easy. So T is equal to K. Now you're going to make use of a constant in your final answer. So L raised to power 1 over 2, M raised to power 0, G raised to power minus 1 over 2. Now we're not going to stop here. We're going to finish this up because we are students of mathematics. A lot can be done here. So to finish this up, remember indices says that whenever you have a square root of a, it can be written as what? A raised to power 1 over 2. Indices also told us that whenever you have a raised to power minus 1, it can be written as 1 over a. If you also have a raised to power minus 2, it can be written as what? 1 over a squared. Don't forget. This is what indices told us. So we're going to try to use what indices told us to solve the above. So from indices, this is k. Now this is going to be square root of L. Anything raised to power 0 is 1. So we have multiplied by 1. Multiplied by, this is going to be 1 over g raised to power 1 over 2. Because of the negative sign. So this t becomes k root of L. Anything multiplied by 1 will give you that thing. So there's no need to add the 1. So this is 1 over. Now applying this here also, we have square root of g. Now our final relation is going to be t equal to k square root of L over square root of g. Now indices also told us that when you have two roots in a division, it can also be written as t. Okay, so our final relation will be t equal to k square root of L over g. Now this is a relation for period. When we go to simple harmonic motion, we're going to talk about this. This is a relation for period of a simple pendulum. This is the length of the loop. This is the acceleration due to gravity. So you see that from this relation, we are able to determine the formula of the relation. You understand? So is there any other thing we are told to find? No. So we have solved this question successfully. If you still find it difficult, go back, rewatch the video, and ask questions on the WhatsApp group if necessary. So the last but not the least, we're going to solve a random example. So they say the van der Waals equation of state can be expressed as P plus A over V squared multiplying V minus B equal to RT, where P is pressure, V is volume, R is gas constant, and T is temperature. Find out the dimension of constant A and B. Now, I need you to pause the video and try to attempt this yourself to see. Now we're going to apply one of the rules. The first rule we're going to apply is let's see. Now, if you observe something, they didn't say constant A and B are dimensionless, because most of us now will be saying, I thought you are not meant to use constant. Now listen, you're not meant to use constant. You're not meant to use coefficients, you understand? But if you are given a constant and it doesn't say that the constant is dimensionless, please use it. From our previous examples, where is that particular example? Yes, from this example, they said k is a dimensionless constant, you understand? It doesn't have a dimension. From the example before it, they said, do you know that this weird looking symbol here is a constant? It's a coefficient or a constant, and we look for the dimension. So if you are given a coefficient, like let's say 2 ps, you're not meant to use this. But if you are given, let's say rho ps, and they say rho is a constant, you can look for the dimension of this. But if they now say rho is a dimensionless constant, then don't use it. You understand the difference now? They'll specify it for you. So now they say A and B are constants, and we're meant to find the dimension. So obviously these constants have a dimension. So to apply one of the rules, remember the first rule, we said that only physical quantities with the same dimensions can be added or subtracted. Meaning that the dimension of this, the dimension of P, they say the dimension of P must be equal to the dimension of what? A over V squared. For you to add it, you understand? Now the dimension of V must be equal to the dimension of what? B. Do you understand? So we're going to try this out to see what we're going to get. Meaning, what's the dimension of P? P is pressure. Pressure is force over area. Dimension of force is MLT minus 2. Area is L square. And this and this is going to go, this is going to remain just L. Now we're going to be left with M, L raised to power minus 1, T raised to power minus 2. Dimension of volume is going to be length times breadth times height, which is L cubed. What else again? Now, for now, ignore these two. We're going to see why. So we just need these two, pressure and volume. So have the dimension of pressure and dimension of volume. So we have the dimension of pressure and volume. Now remember what we said, the dimension of P must be equal to its dimension of A over V square. So if dimension of P is equal to A over V square, meaning dimension of A becomes, when you cross multiply and make A the subject, you have PV squared. So we can quickly solve this. A is equal to PV squared. Let me add this V here. I hope you're not lost. The dimension of P equal to dimension of A over V square. Dimension of A becomes PV square. So the dimension of A becomes P, which is M L minus 1 T minus 2 multiplied by V square, which is L cubed. Dimension of V is L cubed all squared. Now the dimension of A becomes this is M. Now L is L minus 1 T minus 2 multiplied by indices. This becomes L raised to power 6. 3 times 2 gives 6. Some of us might be wondering, okay, you can leave it this way. You can write dimension of P equal to dimension of A over dimension of V square. So that when you make dimension of A the subject, you have dimension of P multiplied by dimension of V square. So you can leave it this way for better understanding. So applying indices, we can have dimension of A to be M L. This is going to be minus 1 plus 6 multiplied by T raised to power minus 2. So the dimension of constant A becomes M L. Now minus 1 plus 6 gives 5. ML 5 T minus 2. So we have gotten the dimension of constant A. Now for the dimension of constant B, they said dimension of constant B is equal to the dimension of volume. So the dimension of constant B is simply going to be L cubed. So the dimension of constant B is equal to L cubed. So we have gotten the dimension of A and dimension of B without even making use of temperature and gas constant. Now for our level, we're not going to be using dimensions of all these higher physical quantity. We just stick to the basics, you understand? So with this, we have solved the dimensions for the various constants.